Hello.
Now it's time for our second remote talk, right? Yes. So while the technical people trying to set up, I see Azalia is already there. I will briefly introduce her. So our next speaker is Azalia Mirhoseini, who's a senior research scientist at Google Brain and advisor at CMORG. She's also co-founder and lead of the Machine Learning for Systems Moonshot at Brain, where they focus on deep reinforcement learning-based approaches to solve problems in computer systems and meta-learning. You can read a lot from her publications, like about the kind of research that she does. She collected many recognitions and awards already, including the MIT Technology Review 35 Under 35 Award. And she did PhD thesis at Rice, where she also won a prize for her PhD thesis. Azalia will start soon, so welcome.
Hello. Hello. Do you hear me?
Yes, yes, we hear you.
Okay. Well, hello everyone. I'm so glad to be here. It's kind of early, at least early for me in California. So I hope you bear with me. So I am going to start my talk in a bit. I can share the slides with you right now. Do you have it? Do you have my slides?
Yes.
Okay.
Yes, we have your slides.
Okay, perfect. So before I start, I was told that I should talk a little bit about my career and how I get to where I am today. I started, I'm from Iran, so I was in Iran until I got my bachelor, and I did so in electrical engineering at Sharif University. And after that, I went to Rice University to get my degree, my PhD degree in computer engineering. When I started, compressive sensing and signal processing was a very hot topic. So a lot of the groups at Rice University were doing this kind of research, and I joined the lab of my advisor, Farinos Hushamfar, and it was a lot of fun doing work at the intersection of electrical engineering, and some sort of a math and signal processing. But shortly after, machine learning became really hot and really popular topic, and I was very, very excited about this topic. So I thought how I can kind of bring machine learning to the type of stuff we were already doing. And a lot of our work was doing research on computer engineering and design automation research. So for my thesis, a PhD thesis, and to bring in machine learning, I decided to do work on machine learning for systems. Just like systems have helped machine learning a lot, so how can we use machine learning to build new systems and build new co-design of hardware and software such that we can run algorithms and machine learning better, faster, and in a more efficient way. So that was my journey during Rice. Back then, a lot of my focus was on more traditional machine learning algorithms, such as L1 regression models and such. My plan always was to become a faculty afterwards. But before then, I thought maybe I spend a year in industry, learn about how things work in the industry, and then I reapply the year after. So for that 1 year, I joined Google Brain. There was this program at the time called Google Brain Residency. It still exists. Now it's called Google AI residency. It was a 1-year program. And the goal of this program was to bring researchers with various backgrounds um, to become highly focused on in deep learning and deep reinforcement learning. To do research in these two fields for about a year and do publications and such. And then later on, it was up to them whether they wanted to stay or go on to do other things outside of Google. So once I joined Google Brain, I had the opportunity to work with a lot of very amazing colleagues, including Jeff Hinton, who is the father of deep learning. And it was a very great experience for me, and that's why I never left. So now it's been almost 4 years that I'm here at Google Brain, and um, uh, after the 1 year of residency, I joined as a research scientist, and then I got promoted about a year and a half ago to senior research scientist. Um, uh, a little bit more of the what I did in Google Brain. So when I joined, I started just doing things that are not exactly related to my background because I just wanted to learn new things. So I worked on um, deep learning models for translation and language models. I also worked on computer vision systems and AutoML, which is a field that has to do with how we learn to design neural network models that can optimize other tasks. So instead of human experts designing these neural network models, we design a meta algorithm that designs subsequent models to solve downstream tasks. But after some time, after about a year or more, I decided that again, machine learning is very exciting. It's a very hot topic, but a lot of success of machine learning is because of the great hardware and systems that we have. So why not return the favor and like develop machine learning in a way that helps us design better systems and chips such that later on they can run better machine learning algorithms. So to this end, with one of my colleagues, Anna Goldie, and uh, we co-founded the Machine Learning for Systems team at Google Brain. And back then it was, and still it's a very new field. Most of machine learning people are very, very excited about computer vision, robotics, NLP and such. But what we did here is to build a momentum and generally make people more aware of systems, and computers are also very exciting benchmarks for machine learning. So, and we started doing some research on that, which I'm going to talk about in a little bit. And during the past 3 years or so, we have been doing continuous research on this domain. We have organized workshops that attracted several hundred attendees. So this is like a very exciting field, and at the same time very important and critical, as I'm going to talk about. It was a very good experience for me to be able to kind of make a case for type of research that I think is important, and make a case for it for other people. So also they also see the value, and they also join me and my co-founder in the way in to enable even more work in this domain. So with that, I'm going to start talking about some of the research, more technical research projects that we have been doing in this field. So a bit more of the motivation. So in the last 10 years, we have seen a surge of models and many, many success stories of deep learning methods. And a big reason for the success of these models are systems such as TensorFlow, PyTorch, and chips such as GPUs and TPUs or tensor processing units. These systems and chips have really made a good platform for machine learning models to run faster and better and more easier by many ML scientists. And our vision is that it is now time for AI and machine learning to really transform the way systems and chips are built. If you look at this chart, take a look at this chart released by OpenAI. There's a very, very interesting trend here. Since 1959 to 2012, there was a 2-year doubling time for the amount of compute used in historic AI runs. Since 2012, with the advent of deep learning, the amount of compute used in the largest AI runs doubled every 3.4 months instead. And by comparison, Moore's law had an 18-month doubling period. So what it shows is that there is a great need for better computer systems and chips if we want to keep up with the increasing computational demand of AI models. Just to give you an example, but it turns out that chip design or system design is not a very easy task. Just to give you an example of how complex it is, here I'm showing you the number of different state spaces which correlates with the complexity of these two games, chess and Go, and that of chip placement. As you can see, the complexities for chip placement, which is only one component of chip design, is orders of magnitude higher than that of these games, these canonical games that are previously solved by AI. So we're dealing with a very complex task if we want to optimize chip design and systems design with AI. Now, in the rest of this talk, I'm going to talk about two of the approaches for using machine learning, and in this particular reinforcement learning, for problems in systems and chips. The first work is reinforcement learning for device placement. So before I jump into that, machine learning, if you look into that, there are three main categories of machine learning. There is supervised learning, which has to do with learning from labeled data. For example, we have an image of a cat or a dog. We want to just classify them. Now, there's unsupervised learning, which is learning from unlabeled data. For example, we have this graph of social network. We want to cluster people or find different social groups across from it. There's no label here, but just by looking at the connectivity, we can solve this unsupervised learning problem by clustering. And then there is reinforcement learning, which has to do this with learning from exploration and exploitations. For example, the game of Go is an example of it, how we train a reinforcement learning agent that can go ahead and play Go and win this game. So reinforcement learning is a very powerful paradigm because many different problem and systems and hardware require decision-making optimization. Here are three examples of it. For example, computational graph placement is when we have a computational graph such as a TensorFlow graph, and we want to place components of it onto the devices, computational devices that we have, such as GPUs, TPUs, and such. And chip placement is another decision-making problem when we have a chip description, netlist, or graph, and we want to place the components of it onto a 2D or 3D grid. Another example is data center resource allocation, when we have all these jobs that are coming into the data center and we want to place it across data center cells and racks. There are many resources for RL in case you're interested to learn about it, but I'm going to just give a higher level idea of what it is and how we use it in the RL for device placement work. In First of all, a little bit motivation of what device placement is and why it's an important problem. So the device placement has to do with taking a computational graph, such as a TensorFlow, a PyTorch, or pretty much any other computer program, and mapping it to the hardware devices that we have. For example, in a lot of deep learning training approaches, we might need several GPUs to run a single model, because we are dealing with a lot of data and we want to run large models on this large amount of data to learn from it. Here are some examples of, for example, Google Translate model, which uses 128 GPUs to train the model. There are other examples on NLP and computer vision that you can see here. Now, traditionally, the way device placement works is has been based on greedy heuristics, meaning that often a human expert sits there and looks at the graph and looks at the available devices that we have. And to do a good job at it, this requires a deep understanding of devices. For example, the way the bandwidth, their memory behavior, latency behavior, the flops, and also requires an understanding of the parallelism and pipelining opportunity in the computational program itself. And there are many heuristics to solve this problem, but often what we see in product is that a human expert is needed on top of those heuristics, and there are several weeks of iterative optimization until optimized placements are found. And usually this does not generalize well, meaning that the problem should be solved, the device placement problem should be solved for every new instance of problem. If we place a vision graph, it doesn't mean that we can just immediately go ahead and place another language graph. Every time we should solve this problem from scratch. So the way we pose this problem as a reinforcement learning problem is that we train a policy, or we can also call it a reinforcement learning agent, that receives this computational graph, in this case a neural network model, and a set of available devices. And the policy outputs an assignment of the nodes of this neural net onto these available devices. Once it's done, we measure the runtime. This runtime can be for just feed-forward path of the neural net. So it's very fast to evaluate. When we have this runtime, we use it as a reward function, as a feedback for the policy, such that next time the policy generates better assignments of or better mapping of this neural net onto the devices. And this loop continues several times until the policy finds optimized solutions. Just a little bit of math here. That's what's happening in this policy. So the policy is parameterized by these learnable parameters theta, that in the beginning, we don't know what these parameters are. They're just initialized with random numbers. But over time, we can guide these parameters and update them with gradient descent using the reinforced equation, which enables us to optimize the reward function. And in this case, the reward function is inversely correlated with runtime of a placement. We always want to increase the reward, and in this case, we want to reduce the runtime. So the reward can be defined appropriately. But the interesting and very powerful thing here is that we are optimizing a non-differentiable reward function, meaning runtime, using differentiable parameters of this policy. Here is an example of how the placement looks like on a NMT or neural machine translation model. For those of you who are familiar with this is a sequence-to-sequence deep neural net where the encoder takes the language takes a sentence in language A, and the decoder outputs the sentence in the target language. And each of these units are an operation in this sequence-to-sequence model, in this case, an LSTM. And each color here, there are 5 different colors, shows a different device. White is CPU, and each of the other colors is a different GPU. And as you can see here, the placements that are found by this RL policy are not very intuitive to a human expert's eyes, but there are some interesting properties still that we can see. For example, the policy learned to put the embedding layer of the encoder and decoder onto the CPU, and we know that this is the right decision because GPUs are not well made for processing the embedding layers. And we see some clusters of similar colors across the placement. But this is a very vast search space, and the policy still finds optimized solution compared to what we had to the manual for the manual placement. Here, what I'm showing you is the amount of GPU workload by doing the placement optimization with RL and by doing the placement optimization using human expert design for each of the GPUs. As you can see, our RL-based placement, without us telling it to that load balancing is a good criteria, it has found to kind of, just by optimizing the reward function or minimizing runtime, it kind of realized that it should allocate similar workloads to each of the GPUs. On the human expert side, this workload allocation were not ideal because because what's happening in this case is that for training this NMT model, almost 2/3 of the computation happens during backpropagation, and this part of the compute is not visible within the TensorFlow code that is written, that is describing this NMT model. So it makes it much harder for a human expert to optimize this, like in this part of the code that is basically not available to it. Another example here is for a vision model. This is an inception model, and these parts that you see here are convolutions within this inception model. And again, it was a very interesting property that the policy found some parallelism between the branches of this model and learned to place these different branches, in some cases, onto different devices. And in this case, we did this exercise of comparing this RL-based placement with a human, with a baseline placement, where what we did was to place the same copy of this Inception v3 onto the 4 GPUs and did a data parallel approach to running this Inception model. Whereas on the left, for the RL-based placement, we did this model parallelism, meaning we took this Inception model and broke it into, and let the policy map it into 4 GPU devices and optimize runtime. And in this case, we were still getting better end-to-end runtimes after the policy converged compared to the synchronous towers or the data parallel approach. But obviously, we were not doing as well on the load balancing parts because the baseline was completely load balanced. But we looked further into it, and what we saw is that the policy in this case is optimizing for the amount of memory copies that are happening between different GPUs. So even though the workload per GPU is unbalanced, whereas the baseline had a very balanced workload, but by reducing the amount of data communication between different GPUs, the policy learns that that way it can optimize the runtime further compared to baseline. Here are some of our results on this. We recently had a paper last year on generalized device placement, where we can train neural networks that can partition or map new unseen neural network at inference time onto computational devices. So we don't need to train an RL policy every time. We just pre-train it and use it um, uh, from at inference time in sub-second to partition new graphs, which is a very exciting, which was a very exciting results for us, and really enabled us to show the benefit of these models in real world applications. Let me see. I want to also quickly mention another work that we have done on machine learning for ASIC chip placement. You saw this graph before, that chip placement is a very difficult task. And what chip placement is that we again have a graph describing a chip. The nodes of this graph have to be mapped onto a canvas. The nodes of this graph are memories and logic gates. They have to be mapped to a canvas such that the total wire length, power, area, and runtime of displacement is minimized. And this is a very complex problem because the problem size is very large. A graph describing a chip usually have millions or billions of nodes in it. We have multiple optimization objectives for displacement problems such as area, timing, congestion, and such. And the true reward function is really expensive. Obviously, we can't build a chip for every placement. And even the EDA tools that analyze these chips are very expensive to run and also take several hours to evaluate. So what we did in this case, again, was to take a reinforcement learning approach to the placement problem. And just like a human expert observes a placement of a chip and fine-tunes it over time, what we did was train a neural network architecture that takes images of the partial chip placement, and it takes new candidate nodes to be placed, and the policy outputs where that new candidate node of the chip should be placed onto the 2D canvas that is available. And in this case, we also got some very interesting results. For example, this is an edge chip that was built by Google. On the left, you see the human expert placement, and on the right, you see our placement. And the area, the purple area here are where the logic gates are, and the green area is where the memory are. And our optimization function here was to optimize approximate metrics such as congestion and bar length, because it was too expensive to measure the true reward functions. And just by doing that, the policy was able to find very optimized reward functions, and also the shapes of these placements were in a way that were the physical designers who worked with us were very excited to see these convex hull, for example, of the standard cells. And they said this is a practice. This is something they often like to see when they place standard cells, but sometimes it's very hard to do. Here is another placement that we did on an actual TPU block. And this was validated pre-tape out. We achieved to this placement in 24 hours, whereas the baselines take 6 to 8 person weeks, and we did so by also getting improvement in wire length and having comparable results on other metrics such as design rule checking. Another interesting direction for us here is that now we can again push for our generalization vision, meaning that we can pre-train policies on some chips, and the policy becomes experience over time, and then we can show it a new chip and ask the policy to basically place this new chip. And that was something that we are pushing for across all the ML4 systems efforts that we have, because we want these models to become more and more experienced over time as they solve new problems. And in this case, where we are showing this, the violent cost for different chip blocks, and the lightest blue color here is pre-trained model, a pre-trained policy that is applied at inference on this target block. So without even seeing this block before, we are able to get reasonable cost, and after further fine-tuning, we can quickly find really high quality placements for these chips. Here is another example of the policy that we trained from scratch on the left for a chip placement, and on the right, we're showing a pre-trained policy that we only fine-tune on a new unseen chip. And it's very interesting that the pre-trained policy already knows how to leave a space in the middle for standard cells of this chip and put the macros around it. Here, I'm showing you some of the results. We work on proxy cost functions, but we can validate our approach with real timing results when at the end of the training, we run these models on real EDA tools. And on roughly 80% of the chips that we have here, you can see some of the examples, but roughly 80% of the chips we've tried, we can get superhuman results, orders of magnitude faster than the baselines that we have. And we're very excited for this line of work that we're doing. And with that, I want to end this talk by talking a little bit more about ML/RL for system and chip design. So the goal of these models is to improve engineering efficiency by automating and optimizing various stages of design, and potentially enabling global optimization. Also, another exciting property of these is enabling transfer of knowledge across multiple problem domains, and also automatically generating design that can explore trade-offs between various objective metrics. And with that, I can conclude my talk here. Thanks for listening.
Let's thank the speaker. Thanks, Azalia, for a very nice talk. Do we have a short question or two for Azalia from the audience?
I think it's very impressive how much better and faster you are. So I come from Intel. I have seen a lot of the transistor placements and chip placements. Do you plan to use that then in Google if you design your chips, or what will you do with these outstanding results?
Yeah, so definitely that's the goal. We have been working with the hardware team since the inception of this project, and that definitely is in our roadmap.
Mm-hmm. Thanks. Another question, maybe? No? You. The present. Okay, so we have a virtual present for you, which is also material, but it will become material once you receive it. So there is a present to be shipped to you by Ahmad and the organizers teams. Here we want to thank you again for contributing to this event, and hope to meet you at some other point in time. Thanks.
Yeah,
Thanks.
Thanks everyone.
Thanks. Bye bye.